Hello, what we are doing today is we're going to look at atoms, but now we're going to quantify a little bit more our discussion of atoms. So we looked at atomic theory and our ideas about subatomic particles, but now we really want to get an idea of what's there, and we want to talk about the numbers, the number of protons and neutrons and electrons and all that stuff, and get masses for them and convert them into usable units, because knowing how many protons doesn't really help me do much in my chemistry lab. So the first number we want to know is probably the most important one to distinguish what an element is, and that's called the atomic number. It distinguishes one type of atom, or one type of atom from another, or really maybe we could say element from another, because it is its number of protons. So when we look at any periodic table, what we'll see, and we'll skip maybe to the periodic table first, is no matter what periodic table, now periodic tables can look a lot different than this one, but they are always going to have this number on the top, or in the top left-hand corner, and what this is that atomic number. It is the number of protons in its nucleus, and that tells us what the element is. So if we take a look at this slide, nitrogen has 7 protons. Anytime you have 7 protons, you have a nitrogen atom. So notice I shifted this over a little bit, clear my dirty screen. But if we go and find nitrogen, notice any periodic table we'll look at, it'll have nitrogen with a 7 up there, because that 7 means it's nitrogen. If we add a proton, which we can't do very easily, at least not in a chemical process, maybe it would be in a nuclear process, but then if you added a proton, you would make oxygen. Now, you can't do that. In chemistry, we do not do that. So the atomic number is very important, because it's not something that changes very easily unless we get again into radioactive systems. So it defines what our elements are. So nitrogen always has 7 as atomic number. That's its number of protons. Hydrogen has 1. That's its atomic number. That's its number of protons. Potassium has 19. And again, when we look at the masses of these protons, remember they're always in atomic mass units, AMU. However, we have to remember as well that there's some neutrons in there, right? So thinking about the neutrons gets us to another number. So we have the atomic number. If we have element symbols, which we sometimes use, we'll have that atomic number, and for whatever reason it's called Z, on the bottom of our element symbol. Now on top we'll have a different number called the mass number. Now the mass number isn't exactly a mass. What our mass number is, it's our number of protons plus our number of neutrons. So in this example, this is sodium, and again, its atomic number is 11. That means the number of protons that it has is 11. It has 11 protons, but it has a total mass number, total number of this you could think of as the stuff in the nucleus of 23. Well, if 11 of those are protons, well, 23 minus 11, that gives us 12. Would be the number of neutrons in that nucleus. So we subtract them to find what's sometimes called the nuclear number, or the number of neutrons in the nucleus. So we have protons and we have neutrons, and those two things added together give us that mass number. Okay, so we have the mass number on our element symbol. That's the number of protons plus neutrons. We have the atomic number that's always going to be on the bottom. That is the number of protons, and then the element symbol is in the middle. Okay, so here's just one more example. Here's gold. Gold has a mass number here of 197, and an atomic number of 79. But one thing you might be thinking is that we don't see these mass numbers on the periodic table very often. And that's true, we do not, because mass numbers are specific to specific isotopes. So this is one isotope of gold, and what I'll tell you is there's multiple isotopes of gold. So normally these mass numbers are not listed on the periodic table. Atomic numbers are, because again they're constant for the element, but mass numbers are not, because different gold atoms can have different mass numbers. Here's an example of an element, lithium. Now if we looked on the periodic table, remember this is the atomic number, so that's how we could find lithium. It is the 3rd element on the periodic table. It has an atomic number of 3, so the number of protons it has is 3. So if you look at any of these images, you'll be able to count 3 P's in there. Some of those P's are hiding, but they're in there. Now notice they have different mass numbers because these are different isotopes. Now, different isotopes are going to have virtually the same chemical reactivity because they have the same number of protons and the same number of electrons. Actually, but they're going to have slightly different masses. And if we get into severe cases, that can kind of affect how they behave. But for the most part, not. So what we could do with these, and what we sometimes do, is we just see how many neutrons they have. So notice 6 minus 3. This one would have 3 neutrons. And again, if you look in the image, you'll count 3 brown neutrons, which I don't know why they made them brown. 4 neutrons. I would have made them pink or purple or some nicer color. And this one has 5 neutrons if we subtract those. So we know the number of neutrons, and we know the number of protons. We know what its atomic number is, and we know what a mass number is. One thing that we can also see from this image is the number of electrons in this atom. Now, the number of electrons for neutral atoms, the number of electrons has to equal the number of protons. Because remember, our protons are positively charged, and our electrons balance out those charges. They're negatively charged. So notice, if this has an atomic number of 3, notice how many electrons it has. 1, 2, 3. If this has an atomic number of 3, well, which they all do because they're all lithium, it has 3 electrons. Okay, that isn't going to change right now. So what else do we want to look? We look at isotopes, we look at neutral numbers. So one thing we want to look at, here are some isotopes of oxygen. So oxygen's on the periodic table. Notice it doesn't have the atomic number for oxygen, but I could look it up. The atomic number for oxygen is 8. I could put little 8s here. So they're all oxygen. They all have an atomic number of 8. Notice they do have different mass numbers, these different isotopes of oxygen. One has 8 neutrons if I subtract them. If I subtract these, this would have 9 neutrons, and the last one would have 10 neutrons. Now notice, the other thing that I could distinguish about these is they're all going to have 8 electrons, and 8 electrons, because these are all neutral elements. They are not charged right now. Now notice other thing they tell us that each of these isotopes is stable, so each of them naturally occur. The important thing is now we're looking right here at this number. This is the abundance. The abundance tells us how, if we take any sample of oxygen, how much of it is these different isotopes. And notice the important thing here is these isotopes aren't in equal abundance. Notice oxygen 16, as we would call it, is by far the most common, followed by oxygen 17, followed by oxygen 18, and then oxygen 17. So this is by far the most common of our oxygen isotopes. Here's another example. This is boron. Again, boron, if we look at the periodic table, has an atomic number of 5. So this boron has 5 neutrons. Also, interestingly, has 5 electrons. Maybe not interesting. 6 neutrons. This one has 5 electrons. Now notice, again, they have the relative abundance. And one thing I didn't talk about in the last one is the number that was above. This is actually the actual mass of a boron 11. So notice it is very close to its mass number, but it's not exactly the same. Now, you might be scratching your head on that a little bit, because remember, protons have a mass of 1 atomic mass unit, and neutrons have a mass of 1 atomic mass unit. So notice, if the mass number was 11, well, you would think, okay, that's 5 protons, so that should be 5 AMU, and it's 6 neutrons, so that should be 6 AMU. So it should be 11 AMU, and notice the actual mass of that isotope is very, very close to 11, but it's not quite. Some reasons it's not quite is because neutrons are actually slightly heavier. There's also some fraction of electrons that are in there. Sometimes they will give us these real masses that we can calculate with. Oftentimes, though, we'll actually just use those mass numbers to calculate what we're going to call the average atomic mass. So the atomic mass, or really we should call this the average atomic mass, is going to be the weighted average mass of all the naturally occurring isotopes of an element. Okay, so the weighted average, that means, if we go back to our last example, that we're going to look at 2 things. We are going to look at the percent it occurs in and its mass. The percent it occurs in and its mass, to try to figure out what this average atomic mass is. And we'll look at why that's important here in just a moment. First, let's look at an example calculation. This one's kind of crazy. This is the average atomic mass of magnesium. And let's see what they did. So there's 3 different isotopes of magnesium. There's magnesium 24, magnesium 25, and magnesium 26. Notice this is actually the atomic number for magnesium, so it has 12 protons. So notice this would have 12 neutrons, 13 neutrons, and 14 neutrons. So notice how they do this weighted average calculation. They take the percent abundance that we're looking at for boron. So magnesium 24 is the most abundant, 78%, 78.9%. 10% is magnesium 25, and 11% is magnesium 26. Now they take those percent abundances and they multiply them by the masses of those isotopes. And now notice here they use really, really accurate masses. So not 24, but 23.98501417, and so on. But it's the percent abundance, notice, times the mass of that isotope. And then they take all of those and add them up to get our average. So why do we want an average atomic mass? Well, the reason is that's how we represent an element. Normally, if we take an element naturally, it is made up of those different isotopes. So we can't really use the mass of any one isotope because it doesn't exist as a pure isotope. These are naturally occurring isotopes. So a sample of magnesium is going to have this abundance of these different isotopes. So we can't assume the mass of magnesium 24 is 24 or even 23.985 because there are two other isotopes present that raise its mass slightly above that. And this mass is actually going to be on most periodic tables, and it is in AMUs. Now that was really a big, messy calculation. Let's try this one for lithium. There's two lithium isotopes, lithium 7, which we would write like this. Actually, there's 3, right? But the other one is in a really small percentage. So there's lithium 7 and lithium 6 that we'd write like this. Now, if they gave us these percentages, we could calculate this at the average atomic mass the same way. We'd take the percentage, and I'm going to write it out a little bit different. So the average atomic mass, I'm going to calculate it this way. I'm going to take that percentage, 92, change it back into a fraction, so 92 over 100 times 7. Because, you know what, the mass of that isotope is pretty close to 7. And I'm going to add it to that percentage, 8 over 100, to change it back into a fraction, again, and multiply it by its mass, 6 AMU. Now, you can pause and you can punch that into your calculator, but what you will find is that gives us that 6.94 AMU, which kind of makes sense, right? Because 92% is lithium 7. So that mass is going to be pretty close to 7, but there's a little bit of lithium 6 in there. So it's going to lower it just slightly below that 7. Now, what this is saying is one thing we want to be aware of when these are being calculated, when we're calculating this relative atomic mass for these individual elements. Again, they are the average mass of the isotopes that are present, but one thing we want to know is that these are all in relation to 1/12 the mass of one atom of carbon-12. So we're assuming that carbon-12 has a perfect mass of 12 atomic mass units, and it is, when we're referring to it, we're referring that, basically we're saying an atomic mass unit is 1/12 of that mass. Just some background there for you. And so now what we're going to go on and do from that is we're going to talk about Avogadro and Avogadro's number and do some mole and mass conversions, but we're going to do this part of the section in a separate podcast.